You don't understand black holes. I know that sounds rude. I'm not trying to be rude. I'm trying to save you 40 minutes of comfortable lies. Because here's what usually happens at talks like this. Somebody draws a funnel, maybe puts a little marble at the bottom, waves their hands about infinite density, and you all nod and go home thinking you understand something. You don't. Nobody does. And the reason nobody does is not because black holes are too exotic, too distant, too alien to make sense of. The reason is that black holes are where the two greatest theories in the history of physics, theories that have both been confirmed to extraordinary precision by experiment, theories that underpin every piece of technology you use today, walk up to each other and throw punches. And neither one wins. That's the truth about black holes. Not the funnel, not the marble, the war. Let me start from the very beginning, because that's the only honest way to do this. I mean, the beginning of the physics, not the beginning of the universe. In 1915, Albert Einstein finished his general theory of relativity, and he handed the world something genuinely unprecedented, a description of gravity not as a force, not as some invisible hand pulling objects together, but as the geometry of space-time itself. Mass tells space-time how to curve. Curved space-time tells matter how to move. That's the whole picture. Elegant, precise, and when Einstein worked out the equations himself, somewhat frightening in what they implied. Because the equations didn't just describe how planets orbit stars. They described, under the right conditions, a runaway collapse. A situation where matter curves space-time, and curved space-time forces more matter inward, which curves space-time further, which pulls more matter in, and the process doesn't stop. It can't stop. The math says it goes all the way. All the way to what, exactly, is a question that will occupy us for the rest of this conversation. Karl Schwarzschild, a German physicist who improbably worked out the exact solution to Einstein's equations while sitting in a World War I artillery trench on the Russian front, Schwarzschild computed in 1916 what happens to space-time around a perfectly spherical, perfectly non-rotating mass. The solution is beautiful, and it contains a problem. At a particular radius, now called the Schwarzschild radius, something goes wrong with the math. The metric, which is the tensor that describes the geometry of space-time, develops a singularity, a point where the equations break down and return nonsense values. Schwarzschild sent his result to Einstein, who replied that it was a magnificent achievement, but that the singularity was surely a mathematical artifact. Nobody, Einstein believed, would ever find a physical situation that produced it. He was wrong. It took the better part of half a century for physicists to accept what the equations were saying, that stars of sufficient mass, when they exhaust their nuclear fuel, do exactly this. They collapse through their own Schwarzschild radius, and something irreversible happens when they do. Here is where it starts to get strange, so stay with me. The Schwarzschild radius for any object is 2 times Newton's gravitational constant times the mass divided by the speed of light squared. For the sun, that radius is roughly 3 kilometers. The sun itself is 700,000 kilometers in radius, so it's nowhere close to its own Schwarzschild radius. It never will be. It doesn't have enough mass, but for stars of roughly 20 solar masses or more, after the core collapse, after the supernova blows off the outer layers, what remains can be crushed below that radius. And when that happens, an event horizon forms. This is the first thing I need you to understand correctly, because almost everything you've heard about it is subtly wrong. The event horizon is not a wall. It is not a surface. It is not a place where something is sitting. It is a boundary in space-time defined entirely by future light cones, by the fact that beyond it, every path that any particle or photon can take, every physically possible trajectory, points inward, not because there's something blocking the way out, because outward is no longer a direction that exists. I want you to sit with that for a second, because I find that people nod at it too quickly. You fall through the event horizon of a large black hole, and I'll explain why large matters in a moment. And you feel nothing. No wall, no jolt, no alarm. If the black hole is large enough, the tidal forces at the horizon are gentle. You cross it, and your local experience is entirely normal. You could be reading a book. You would not know, from any local measurement, that you had crossed the horizon. And yet something has changed absolutely. You have entered a region of space-time from which no causal signal can ever reach the outside universe. Your future is entirely contained within the black hole. You will eventually be destroyed. We'll get to how and where, but the horizon crossing itself is mundane. That is deeply unsettling to most people because we like our catastrophes to announce themselves. Black holes don't. They are polite about it. Now, here's a thought experiment I want you to run. Imagine you have a friend. Let's call him Bob. Bob is watching you fall toward the black hole from a safe distance, from far away. From Bob's perspective, something very different happens. Because of the extreme warping of space-time near the horizon, light signals from you get progressively redshifted and time-dilated. Bob sees you moving slower and slower as you approach the horizon. He sees your clock running slower, your image getting redder, your motion asymptotically approaching but never quite reaching the horizon, freeze-framing, dimming, fading. From Bob's perspective, you never cross the event horizon. You just hang there getting dimmer for the rest of the universe's history. Two observers, one event, two completely incompatible accounts of what happened, neither one wrong. And this is not a paradox of imprecision or measurement error, it is a fundamental feature of general relativity. The question of what really happened is not a question that general relativity can answer in any observer-independent way. And that should bother you because we have been trained to believe that physics is supposed to give us answers that don't depend on who's looking. I've been thinking about this for more than 40 years. My first serious engagement with black holes was not in a seminar room, it was in an argument. When I was a young physicist, the black hole was treated as a kind of thought experiment made real an extreme limit of general relativity that we could study with general relativity's tools. And that was that. The quantum mechanics of what happened inside, or at the boundary, was not considered a serious program of research. It was considered speculation. Stephen Hawking changed that. In 1974, Hawking published one of the most remarkable papers in the history of theoretical physics. He showed, using a combination of quantum field theory and the curved space-time geometry of general relativity, that black holes are not black, they radiate. They emit thermal radiation with a temperature inversely proportional to their mass, now called Hawking radiation. And they do so continuously, losing energy, shrinking over astronomical timescales, and eventually, Hawking argued, evaporating completely, leaving nothing behind. This result was so surprising that when Hawking first told people about it, his colleagues thought he had made a mistake. He hadn't. He had found something real, and in finding it, he had planted a bomb in the foundations of physics. Here's why. Quantum mechanics has a rule. It is not a guideline. It is not a default assumption that can be overridden by special circumstances. It is a mathematical law built into the deepest structure of the theory. The rule is called unitarity. And what it says is that information is conserved. If you know the complete quantum state of a system at one moment, you can, in principle, following the equations backward, recover the complete quantum state at any earlier moment. Information doesn't disappear. It may be scrambled, it may be encoded in ways that are practically impossible to decode, but it is preserved. The past is always recoverable from the present in principle. That is what unitarity requires. Now, Hawking radiation is thermal. It is random. It carries no information about what fell into the black hole. It carries no imprint of whether you threw in encyclopedias or rubber ducks. And if the black hole eventually evaporates entirely, leaving nothing behind, then all that information, the complete quantum state of everything that ever fell in, is gone, destroyed, not scrambled, not hidden, gone. That is a violation of unitarity. That is a violation of quantum mechanics. And you cannot have that. You cannot have a theory of physics that conserves information in every experiment ever conducted on Earth and then throws that law away when a black hole is involved. Something has to give. Now, here is where it gets genuinely strange. This is the point where I have to tell you about a period in my career that I still think about, not with nostalgia, but with something closer to adrenaline. For roughly 2 decades, Hawking and I disagreed, publicly and sometimes sharply, about what the resolution to this paradox was. Hawking believed that information was genuinely destroyed, that this was a new law of physics, a black hole exception to unitarity, and that we should revise quantum mechanics to accommodate it. I believed he was wrong. Not because I had a clean solution, I didn't, but because the alternative was worse. If information can be destroyed in black holes, then the entire framework of quantum mechanics, which makes definite predictions because it conserves probability, which makes chemistry and atomic physics and particle physics possible, becomes an approximation that breaks down under certain conditions. And if it breaks down there, you have no way of knowing where else it breaks down. You have lost your grip on the theory. I could not accept that. Let me give you the thought experiment that crystallized this for me. Imagine you take a book, let's say it's a book of poems, and you burn it. Has the information in the book been destroyed? Your first instinct is yes, but it hasn't. If you could collect every single photon and gas molecule that escaped during the burning, every ash particle in exact position and velocity, the complete microscopic state of the universe after the burning contains, encoded in incredibly complex correlations, everything that was in the book, you could in principle reconstruct it. No information is destroyed. The laws of thermodynamics tell you that it's practically impossible to decode. The entropy is increased. The information is maximally scrambled, but it is there. Now try to tell me the same story about a black hole. You drop the book of poems into a black hole. The Hawking radiation comes out random, thermal, uncorrelated. The black hole eventually evaporates. Where is the information? Hawking said, nowhere, gone. I said, it has to be somewhere. It has to come out in the Hawking radiation, encoded in quantum correlations so subtle they look thermal to any ordinary measurement, but present. The real question was how. How does information that fell through an event horizon, a one-way door, get back out? The answer came from an unexpected direction. In 1993, Gerard Hooft, one of the great physicists of the 20th century, proposed something radical, and I developed it further with Leonard Susskind and others into what became the holographic principle. Here is the idea. Take the event horizon of a black hole. It is a two-dimensional surface, a sphere surrounding the collapsing mass. The Bekenstein-Hawking entropy formula, which Hawking himself had derived, says that the entropy of a black hole, the number of bits of information it contains, is proportional not to its volume, but to the area of its horizon, not the three-dimensional interior. The two-dimensional surface. That is a shocking statement. In ordinary thermodynamics, the entropy of a system scales with volume. A box twice as big contains twice as many particles, so it has roughly twice the entropy. But for black holes, entropy scales with area. What this is telling you is that the maximum amount of information you can pack into any region of space is not determined by the volume of that region, but by the area of its boundary measured in units of the Planck area, which is roughly 10 to the minus 66 square centimeters. Everything that can ever happen inside a region of space is somehow encoded on its surface, like a hologram, a three-dimensional image encoded on a two-dimensional film. The physics of the interior is, in a deep and not fully understood sense, equivalent to a different physics playing out on the boundary. This is not a metaphor. This is a conjecture with powerful mathematical support. And in string theory, it has a precise realization called the ADS CFT correspondence, in which a theory of gravity in a certain curved space-time is exactly dual to a quantum field theory with no gravity living on the boundary. Exactly dual. Same physics, same predictions, different description. The implications are astonishing, and I want to be precise about what they are and what they are not, because this is where people start making claims that go further than the physics warrants. The holographic principle does not say that reality is a simulation. It does not say that the universe is literally a two-dimensional object. What it says is that the complete description of physical reality in some region is captured by degrees of freedom on its boundary, and that is a statement about the structure of information in physics, not about the metaphysics of what's real. But it is a real statement. It has consequences. One consequence is that the interior of a black hole is not, from the perspective of the holographic description, a separate place where information is trapped. The interior degrees of freedom are encoded in the horizon degrees of freedom, and the Hawking radiation is a form of information transfer from those horizon degrees of freedom to the outside world. The information is preserved. Unitarity is maintained. Hawking was wrong about information destruction, and in 2004, under considerable pressure from the evidence accumulated by that point, he publicly conceded the bet. I want to be fair to him. It was a graceful concession. He was a great physicist, and great physicists are capable of changing their minds. But I'd been saying it for 30 years, and I'll admit I felt something when he finally agreed. Not triumphant, more like the feeling after a very long argument when someone finally says, "All right, I see it." But here is the thing I have to tell you now, and this is where the intellectual humility part comes in. And I am not saying this to be modest or to hedge my claims. I am saying this because it is the true state of affairs, and you deserve to know it. We do not know the mechanism. We know that information must be preserved. We know the holographic principle is almost certainly correct. We have the ADS CFT correspondence, which is a beautiful and precise mathematical structure. What we do not have, what no one has, and what keeps people up at night who think seriously about this, is a picture of what actually happens at the horizon, concretely, physically. In terms of degrees of freedom, we understand. In 2012, Ahmed Almhiri, Donald Meroff, Joseph Polchinski, and James Sully published a paper that is now referred to in the literature as AMPS, the firewall paper. And what they showed in careful and devastating detail is that if you take seriously both the requirement that information escapes in Hawking radiation and the requirement that an observer falling into a black hole experiences nothing unusual at the horizon, you get a contradiction. Specifically, if Hawking radiation is fully entangled with the information of what fell in which it must be for unitarity to hold, then the early and late Hawking radiation must be maximally entangled. But quantum mechanics does not allow a quantum system to be maximally entangled with two different things simultaneously. The so-called monogamy of entanglement. So if the outgoing Hawking radiation is entangled with the earlier radiation, it cannot also be entangled with the infalling modes just inside the horizon, the entanglement that in standard quantum field theory in curved space-time produces the smooth vacuum at the horizon. Break that entanglement and you do not get a smooth horizon, you get something energetic, a wall of high energy quanta, a firewall, and an observer falling in would hit it and be incinerated rather than crossing smoothly through nothing. This is where I'm going to be completely honest with you about where I stand, and where I stand is uncertain. The firewall argument is, as far as I can tell, correct within the assumptions it makes. The problem is that we don't know which assumption to give up. There are several options. You can give up the smoothness of the horizon, accept the firewall, and then you have to explain how an observer outside and an observer inside can have such radically incompatible experiences without violating any principle of physics. The outside observer sees the information come out gradually in the Hawking radiation. The inside observer is incinerated at the horizon. These are not compatible with the equivalence principle of general relativity, which says that falling into a gravitational field is locally equivalent to being in free space. Einstein's principle, one of the pillars, you can give it up, but then you're tearing out a load-bearing wall. Alternatively, you can try to rescue the smoothness of the horizon by invoking something called black hole complementarity, the idea that the two descriptions, infalling observers and outside observers, are complementary in the quantum mechanical sense, like position and momentum, and can never both be verified simultaneously. I spent years developing this idea, and I still think it captures something important, but the AMPS argument suggests it may not be enough on its own. And there is a third possibility, which goes by the name ER equals EPR, a conjecture by Juan Maldacena and Leonard Susskind that entanglement between quantum systems is, in some deep sense, the same thing as a geometric connection through spacetime, a wormhole. That if two Hawking quanta are entangled, there is literally a tiny wormhole connecting them. It is a wild idea. It is the kind of idea that when I was a young physicist, I would have laughed at. I don't laugh at it now. The mathematics is too interesting. The connections run too deep. Well, let me give you a third thought experiment, because I think it cuts to the heart of what is actually at stake here. Imagine a library, an enormous library, containing every book ever written, every piece of information humanity has ever produced. Now imagine you build a wall around the library. Not a wall you can see through an opaque boundary. From outside the wall, you can receive signals that bounce off it, but you cannot go in and look at the shelves. My question is this: does the library still contain information? Your instinct says yes, obviously. The books are still there. But what the holographic principle is telling you is something more radical. It's telling you that the complete physical description of everything inside that library is contained in the pattern of degrees of freedom on the wall itself. That the interior is, in some precise sense, redundant. The wall is not a summary of the library. The wall is the library. This does not mean the books are an illusion. It means that the distinction between interior and boundary is not as fundamental as our three-dimensional intuitions suggest. And if that is true for a library, it is true for any region of space, including the observable universe itself, which has a cosmological horizon, a boundary beyond which we cannot receive signals. The holographic principle applied to cosmology suggests that everything we see, everything we know, the entirety of accessible physical reality is encoded on a two-dimensional surface, somewhere roughly 45 billion light years away. I find this wonderful and vertiginous and deeply unresolved. I want to say something now about the history of this subject that doesn't get said enough, because the popular account tends to present it as a series of triumphant discoveries: Schwarzschild's solution, Hawking's radiation, the holographic principle, with each step building cleanly on the last. It didn't happen that way. It happened in arguments. John Wheeler, who coined the term black hole in 1967, spent years trying to persuade the physics community that gravitational collapse was real, that the singularities in the equations describe something physical and not merely mathematical. He was not universally believed. The great Russian physicist Lev Landau thought collapsing stars would find some way to stop. Einstein himself, and I keep coming back to Einstein because it is genuinely remarkable, Einstein published a paper in 1939 arguing that black holes couldn't form, that orbiting matter would reach the speed of light and stop the collapse before the Schwarzschild radius was reached. The argument was wrong, and it was wrong in a way that's almost poignant. Einstein didn't fully trust his own equations. He thought the perfect sphere, zero angular momentum idealization, was too unphysical to give real results. He kept expecting reality to restore order. It didn't. Roger Penrose proved in 1965 that singularities were not an artifact of perfect spherical symmetry, they were generic. If enough mass collapses, you get a singularity. The math is unambiguous. Einstein died in 1955, a decade before the proof. He never had to reckon with it directly. Sometimes I think that's a mercy, and sometimes I think what a conversation that would have been. And Hawking. I want to say something serious about Hawking, because his role in this story is complicated by the way he has been mythologized. Hawking radiation is a genuine, immortal contribution to physics. It will be correct in some form, in whatever theory of quantum gravity we eventually construct, because it follows from general properties of quantum field theory in curved spacetime that are robust. His intuition about the area theorem that the total area of black hole horizons in any process can never decrease, uh, analog of the second law of thermodynamics, that too was profound and correct and led directly to Bekenstein's entropy formula and to everything that came after. But Hawking was wrong about information. And he was wrong about it not because he made a calculation error, but because he trusted the semi-classical approximation quantum fields on a classical curved space-time background past the point where it should be trusted. The approximation works beautifully far from the Planck scale. But when you ask what happens to a black hole over its entire evaporation lifetime, you are probing regime after regime of physics, including the late stages when the black hole is Planck-sized, and the approximation has long since broken down. Hawking extrapolated from a regime where his calculation was valid to a conclusion that required physics he didn't have. That is a human error, a very common one among brilliant people. I have made versions of it myself. The correction is not a criticism of the man, it is how physics works. Let's talk about what's inside. I said I'd come back to this, and I will, but I want to be careful. When you fall through the event horizon, assuming no firewall, general relativity predicts that you will eventually reach the singularity. The singularity is not a place. This is crucial and almost universally misunderstood. In the space-time geometry of a black hole, the singularity is in your future. You cannot avoid it for the same reason you cannot avoid next Tuesday. Once you're inside the horizon, the singularity is where time goes. It is a place in time, not a place in space. And when you reach it, the tidal forces, the difference in gravitational acceleration between your head and your feet, become infinite. You are stretched into a filament of matter, a process that relativists call spaghettification with what I can only describe as unseemly cheerfulness, and you are destroyed. Your mass energy contributes to the singularity. And here's the thing about singularities. They are not physical, they are mathematical signals that general relativity has been pushed past its domain of validity. The theory is telling you, in the only language it has, that some other physics must take over at scales smaller than the Planck length, about 10 to the minus 35 meters. What that physics is, we do not know. A complete theory of quantum gravity would resolve the singularity, would replace it with some finite, regular, quantum mechanical description of what happens to matter at extreme density. We do not have that theory. We have candidates, string theory, loop quantum gravity, causal dynamical triangulations. Each of them handles singularities differently. Each of them has features that are appealing and features that are unresolved. None of them has been confirmed by experiment, and some of them cannot be at energy scales accessible to any foreseeable accelerator. The singularity, in the honest assessment, remains our most visible symbol of ignorance about the deep structure of spacetime. Now I want to come back to something that has been building in this conversation, something I've been circling around without quite saying directly, and I want to say it now. The problem of black holes is not really a problem about black holes. It never was. It is a problem about the relationship between quantum mechanics and gravity, two theories that have coexisted for a century without being reconciled, that work with extraordinary precision in their respective domains, and that are fundamentally incompatible at their foundations. General relativity describes space-time as a smooth, continuous, classical manifold. Quantum mechanics describes physical systems as existing in superpositions of states, with discrete energy levels, with entanglement, with the irreducible uncertainty of the Heisenberg principle. These two descriptions use different mathematics, different conceptual frameworks, different notions of what a physical state even is, and they have to be reconciled because the universe cannot actually be split into regimes where one theory applies and the other doesn't. There is one universe, and somewhere there must be one theory that describes it. Black holes are the most spectacular place where the two theories are forced to coexist, forced to give incompatible answers, forced to expose the gap in our understanding. Every question we've examined tonight, the information paradox, the firewall, the nature of the singularity, the holographic principle, is a different angle of approach on the same enormous problem. Here is what I think is true, And I want to be careful to distinguish between what I think and what I know, because they are not the same thing, and a physicist who can't tell the difference is dangerous. I think information is preserved. The holographic principle tells us it must be. The ADSIS, CFT correspondence, which has been tested in hundreds of different ways within the domain where it applies, shows us concretely how a theory with gravity can be exactly dual to a theory without gravity, and in that duality, information is manifestly preserved. The only sensible conclusion is that information escapes in Hawking radiation, encoded in correlations that look thermal but aren't. I think the firewall paradox is real and not yet resolved. Something has to give, and we don't know what. I think the holographic principle is one of the deepest things we know about the universe, that three-dimensional space is not fundamental, that information lives on surfaces, that our intuitions about volume and containment and inside and outside are approximations to some deeper truth we haven't yet formulated. And I think that formulating that deeper truth, actually writing down a consistent theory of quantum gravity, understanding what space-time is made of at the Planck scale, resolving the singularities, is the hardest and most important open problem in theoretical physics. It has been for 50 years. It may be for another 50. Let me tell you about a moment in my own work that I've never quite gotten over. It was in the early 1990s when the holographic principle was still a very new and very strange idea, and I was trying to understand how it could possibly be consistent with a falling observer's experience. You have someone falling into a black hole, and from the outside you're computing in holographic terms, everything is encoded on the horizon. The Hawking radiation is carrying out information, unitarity is preserved. But the falling observer sees nothing unusual. She crosses the horizon, she reads her book. For her, there is an interior, there are degrees of freedom inside the black hole, there is a three-dimensional world. Both descriptions have to be physically valid. And I realized this took me a long time, longer than I'd like to admit, that what we were dealing with was something that quantum mechanics already knows how to handle. Complementarity, Bohr's complementarity. Position and momentum are both real observables of a quantum system, but they cannot both be measured simultaneously. They are complementary descriptions. A photon is both a wave and a particle, but you cannot design an experiment that reveals both aspects at once. What I was seeing in black holes was a new gravitational form of complementarity. The interior description and the exterior description are both physically valid, but they are complementary. No single observer can have access to both. The observer outside can, in principle, reconstruct everything from the Hawking radiation. The observer inside can describe the interior geometry. Neither can do both. And the consistency of physics requires that no experiment, no matter how clever, can put both descriptions in the same lab and find a contradiction. I called this black hole complementarity, and the moment I understood it clearly, around 3 in the morning in my office with a whiteboard covered in calculations, was one of the most genuinely exciting moments of my scientific life. Not because I had solved the problem, but because I could see for the first time what shape the solution had to have. That is a different feeling from having the answer, and in some ways it's more clarifying. There is a question I haven't answered, and I want to address it because some of you are surely thinking it. What is a black hole actually made of? Not in the naive sense, not what kind of matter is inside, because we've established that the singularity is a breakdown of description and not a physical place in the ordinary sense. I mean, what are the microscopic degrees of freedom? If a black hole has an entropy proportional to the area of its horizon, if Bekenstein's formula is right, and it is, then that entropy corresponds to an astronomically large number of microstates. For a black hole of 1 solar mass, the Bekenstein-Hawking entropy is about 10 to the 77 bits. Those are real degrees of freedom. What are they? In string theory, there is a partial answer. For certain special black holes, called extremal black holes, in certain string theoretic settings, one can count the microstates explicitly. The entropy can be derived by counting configurations of strings and membranes, and it matches the Bekenstein-Hawking formula exactly. Strominger and Vafa did this in 1996, and it was a triumph of string theory. But it applies to a restricted class of cases, and the general answer, what are the microstates of a realistic astrophysical black hole, remains unknown. The degrees of freedom live somewhere on the horizon. We know that much. But what they are, how they relate to the ordinary degrees of freedom of matter, what happens to them during evaporation, this is genuinely unsolved. The black hole's microscopic constitution is as mysterious as the electrons were before quantum mechanics. And that comparison is not accidental. The resolution of the electron's mysteries required a revolution in physics. I expect the resolution of the black hole's mysteries to require another one. I want to say one more thing about the observational situation, because this conversation has been almost entirely theoretical, and that can leave you with the impression that black holes are purely abstract objects. They are not. We have now imaged the shadow of supermassive black holes, first M 87 times in 2019, then Sagittarius A times at the center of our own galaxy. We detect gravitational waves from binary black hole mergers with LIGO, and the waveforms match general relativity's predictions with extraordinary precision. These are real objects. The Schwarzschild radius is real. The event horizon is real. And while the Hawking temperature of an astrophysical black hole is far too small to detect for a solar mass black hole, it's something like 60 nanokelvin, dwarfed by the cosmic microwave background analog systems in the laboratory, have observed Hawking-like radiation in sonic black holes, where the speed of sound plays the role of the speed of light. The physics is not hypothetical. It is out there, operating, forming in the cores of massive stars, sitting at the centers of galaxies, merging in pairs and radiating space-time ripples across the universe. The theoretical difficulties I've been describing are not reasons to doubt that black holes exist. They are reasons to understand that we don't yet have a complete description of what they are. There's a difference, and it matters. So where does this leave us? Let me try to say it plainly. We know that black holes form. We know they have event horizons. We know that quantum mechanics predicts Hawking radiation, and that if Hawking radiation exists, as it almost certainly does, even if we can't measure it directly, then the information paradox is real and must be resolved. We know the holographic principle is probably correct, which means the nature of three-dimensional space is more subtle than it appears, which means quantum gravity will not merely be a quantization of general relativity, but will require us to rethink what space itself is made of. We know that the singularity is a signal of ignorance, not a physical place. And we know that none of the pieces fit together yet into a single coherent story. The black hole is a machine that takes in our two greatest theories and outputs contradictions, not because the universe is inconsistent, because we are not yet smart enough to see how it is consistent. This is where physics stands, not at the end, not even at the beginning of the end. At the end of the beginning, with the shape of the problem finally clear, with the tools being built, with a generation of physicists who take quantum gravity seriously, not as philosophy, but as science, and who have real mathematical structures, the holographic principle, string dualities, the ADS-CFT correspondence to work with. The contradictions are the progress. The fact that the paradox is sharp enough to generate papers is itself a sign that the field has matured. I have been arguing about this for my entire career, and I'm going to tell you something that I don't say very often. I love it. I love that black holes are hard. I love that the event horizon is where our best theories come to fight. I love that a question about astrophysical objects 4 billion light years away connects by rigorous argument to questions about what space is made of, what information is, whether the universe has a boundary, whether three dimensions are real or emergent. That chain of reasoning from observation to mathematics to deep structural question is the thing that makes physics worth doing. Not the answers, the structure of the questions. The fact that asking the right question about a black hole forces you by pure logic to ask what reality is made of. That's not a metaphor. That's not poetry. That's how physics works when it's working right. And here is the thing I want to leave you with. Not a summary, not a conclusion, a question that I find genuinely disturbing in the productive sense of that word. If the holographic principle is correct, if the complete description of everything inside any region of space is encoded on its boundary, then what is the boundary of the observable universe encoding? The observable universe has a cosmological horizon, a surface beyond which we cannot receive signals. The holographic principle says everything we see, everything we know, everything physics has ever described is encoded on that surface, not as a metaphor, as a physical statement about where the degrees of freedom actually live. And if that's true, then our three-dimensional experience, this room, these people, the distance between me and you, the fact that space seems to have extent and depth and volume, all of that may be emergent from a two-dimensional description that we haven't written down yet. The question of what that description is, how it gives rise to space-time, why it gives rise to this space-time with these laws, that is the question that I think will define physics for the next century. It is not answered. It is barely well posed. But the black hole is the chisel that carved it. Every sharp question we have about quantum gravity was sharpened by thinking hard about what happens when too much matter falls into too small a space. The black hole is not a mystery on the edge of physics. It is a mirror held up to the center of it, and what it reflects, we are only beginning to see. Approximatel.